Now let's properly define all the properties of waves. Things we can talk about are like the medium, wavelength, frequency, amplitude, and period. Yes, we'll go over this, but I think it's nice to see this visually first. So let's pull up the webcam. Hello. And I've got a rope that I've tied off. Right? So let's do some basic waves. I can do up and down. Right? And I just oscillate. I am transferring energy by saying a wave that way. Right? There it transfers. Now, we're kind of missing some details, so we're going to generate standing waves. I'm just going to twist this around. So this would be a low energy, right? It's very slow. What do I mean by the wavelength? The wavelength is the distance going from peak to peak. On this, what you're seeing right now is actually be half of a wavelength. You're only seeing one peak. You have to go to another step over to see the next. So let's go to seeing a full wavelength. I'm going to up the frequency. There we go. I've increased the frequency, and now you can see one wavelength, just the distance between the two peaks in this standing wave. Right? So, key insight here. The frequency went up, the wavelength, it got shorter. All right, let's see if I can get 3 troughs in here. Let's try and get 3. And, nope, that's 2 again. Let's go for 3. Almost there. There we go. So there's 3. Right? You're seeing about 1 wavelength and a half. The wavelengths keep getting shorter and shorter now. The frequency, that's going up. The frequency has increased. So every time I drop the wavelength, the frequency correspondingly must increase. Another thing you notice, I'm putting a lot more work into here. It takes a lot more energy. Remember, bring this to a stop. Right? Here's a low energy. It's very easy. When I try and go for 3, I have to work really hard. It takes a lot more work, a lot more energy to get the 3 nodes. So, things to emphasize here. Right? Wavelength decreases, the frequency, the number of oscillations per second goes up. And as the frequency goes up, the energy, the amount of work it takes for me to keep it going, goes up. Energy and frequency are proportional to each other. All right? Now let's come back down to the slides.
Coming back to our wave properties now without using the rope as an example. We have the wavelength. That is a distance measurement and is a distance from peak back to peak. Similarly, trough to trough. Right? Key thing, wavelength, we label with a lambda, and it is a measurement of distance, meters. Frequency, that is the number of oscillations in a given second. Think of how often the rope would go up, down, up in 1 second. Right? That's your frequency. Inversely related to the frequency would be the period, just the time it takes for one oscillation. So frequency and period are just literally inverses of each other. If I do 1 over the frequency, I'll have calculated the period. And the last one to talk about, amplitude. That's just the height of the wave. Turns out this one's not going to matter a whole lot for us, so I'm not going to emphasize it much beyond this point. Finally, light is a special type of wave, and we're going to construct why it is. But to get there, we need to discuss that medium thing. When you hear me speak right now, what's happening? There are pressure waves being generated by your speakers. Right? Your speakers are taking air that's around it and going for high density, low density. Think of going, right? You have regions of high pressure, low pressure, high, low, high, low. That's a wave. And so that wave propagates through the air, and that will cause the anvil in your ear, the bones in your ears, to oscillate in response to these changing pressures, which your brain then interprets to be sound. Similarly, have you ever tried going for a swim and talking to your friends underneath the water? Right? you still can communicate. Sound's still traveling, but the speed that sound wave is traveling through, is moving at, changed just because you went from sound in air versus sound in water. So this is the concept we mean about medium. What is the medium that the wave is traveling through? And now that will tie back into why light is a special type of wave. Because what is the medium that light travels through? Any of you old school Alien fans might have heard the phrase, the tagline, in space no one can hear you scream. Right? What they're referencing that is that when you're in the vacuum of space, there is no sound to propagate. Right? There is no medium out in space for sound waves to travel through. And yet, light gets to travel through the vacuum of space. Why does light get to move through nothingness? Right? So to answer that, we need to build up the special properties of light. Before I can answer that question about what's so special about light traveling through the vacuum, we need to build up our electric and our magnetic models. So this is going to be a short, single slide version. This is literally lectures, an entire course worth of material, but we just want the surface details to answer some questions. For starters, we can talk about the electric force, also known as Coulomb's law. And this should look very familiar to you. It says the electric force between two charged objects is the Coulomb's constant, charge of object 1, charge of object 2, and the inverse square distance between them. Looks exactly like the law of gravity. The only difference is that instead of masses, you have charges. And instead of gravitational constant, you have what's called Coulomb's constant, this 8.99 10 to the 9th Newton meters per Coulomb squared. Coulomb being the unit of charge instead of kilograms for mass. Right? So here's the things to emphasize here. 10 to the 9th. Big G, that universal constant, was 10 to the minus 11th. So already I can start to make this claim here that the electric force is orders of magnitude stronger than gravity. This is going to matter a lot for us later in the semester. Right? Now, let's look at this. Right? I can talk about having we'll say red is a positive charge object, blue is a negative charge object. So if I have opposite charges, they attract. If I have like charges, positive, or negative with negative, they will repel. So unlike gravity, electric forces can be attractive or repulsive forces. Now we can talk about magnetism. And once again, this is going just the brief hands-over cursory view. But when we talk about magnetism, think of your toy magnets. How many of you have had, say, the two refrigerator magnets, and you try and slide one across the table by bringing the north pole of one towards the north pole of another, and they will repel. Well, eventually you'll get your magnets too close. One pole will flip around. You'll have north and south poles attracting, and they stick together. Right? Another thing you do is visualize the magnetic fields. Right? So here's our magnet, and you can see a north and a south pole. And you see if we were to sprinkle iron filings over this magnet, the iron would line up in shape of these magnetic fields. So remember previously we've discussed how people were worried about Newton's law of gravity because it described this action at a distance thing. Right? How does gravity act? How does the sun's gravity hold the earth in orbit? There is no string, there is no rigid object holding us together. So how can we push on each other at these distances? Fields was this concept to try and explain that, try and convey these things. So when we talk about electricity and magnetism, we're often going to try and discuss these fields. And think of the fields as what's happening around a magnet or a charged object. So before we move on, quick question for you. What are the 3 ferromagnetic elements? As in, if you took a magnet and you wanted to stick it to a piece of metal, there are only 3 natural ones that magnet will stick to. Right? Here they are. It is iron, cobalt, and nickel. That is it. Anything else is either a alloy. Steel often gets cited as being a ferromagnetic material, but steel is a alloy of iron and carbon, the carbon to make it stronger. Right? So these are the only three that are naturally ferromagnetic. So now let's shift towards a nice little demo to talk about some strange properties of what we're going to call magnetic induction.
So we've established that the only three types of elements that are ferromagnetic is iron, nickel, and cobalt. So I'm going to take a aluminum pipe and I'm going to drop a magnet down it. All right, so quick tests. Right? Aluminum, magnetic or not? Not. Just doesn't stick to it. Let me convince you. Yes, it is a real magnet. All right. So, for reference, I'm going to take a non-magnet now and just drop it down this pipe. You're looking for the time it takes. It's going to be a big whir. It's just going to be a blur as it drops down here. Right? So here's the non-magnet down the aluminum pipe. Right? Too fast. Can't really see it. Let's try the magnet down the aluminum pipe. For reference, nothing's happening. But as soon as I drop it down the pipe, why did it take so long? Try that again. Right? Non-magnet down the pipe. Fast. Less than a second. The magnet down the aluminum pipe. What gives? Why is it taking so long? This is our electromagnetic induction.
All right, time for the formal definition. Electromagnetic induction just says that if there is a changing magnetic field, it will induce an electric field. Similarly, if there is a changing electric field, that will induce a magnetic field. So think back to that aluminum pipe when the magnet is falling down it. The magnet doesn't stick to aluminum. Aluminum is not a magnetic material. But when that magnet is falling through the pipe, as it falls down the pipe, that magnet will have a changing magnetic field. The pipe is feeling the magnet move. So in response, that aluminum pipe will generate an electric field. An electric field that's going in circles trying to push up the magnet. Because it turns out that all materials do not like magnets moving around. We try and prevent that motion. We oppose the change. So we're going to have this induction. Magnetic fields inducing electric, and electric fields inducing magnetic. And it's all this game. And all you need is a changing one. If one changes, the other is created. Another example of this, how your credit cards work if you're still using a swipe versus a chip reader. Right? What your credit card is doing is it's a bunch of strips of north-south poles. North pole, south, north-south. And you have a unique key, a unique credit card by saying take this pole and flip it around. So when you swipe through the machine, the machine will see north, 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 south, north, 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 north. Right? Well, that can be translated into a code that goes to just your credit card, your bank account. And so by choosing the orientation of these north and south poles, you can create a unique credit card. Hence, everyone can have their own cards that they can swipe through and exploit the electromagnetic induction to charge their card or charge their money. Tying all these field concepts together, we can say that light is a combination of an electromagnetic wave. Here's a picture. Have an electric field that's oscillating. We'll have an electric field that grows in strength, then decreases, and then grows again. Right? Think of this electric wave oscillating up and down like the rope from earlier. Okay? Well, by the induction rules, if there's an electric field that's changing as it gets stronger or weaker, that must induce a magnetic field that's also changing. So our magnetic field will go out, in, out, in, out. While this electric field goes up, down, down, up, so on and so forth. And so that combination of the changing electric and changing magnetic waves propagates in this direction at the speed of light, 3 times 10 to the 8th meters per second. This is what we mean, that light is a electromagnetic wave. Finally, the unique property about the electromagnetic waves is that they are their own medium to propagate. Remember that I was talking about earlier with sound waves. You can't hear in space because there's no medium there. Light gets to travel through the vacuum of space because as it propagates through space, it's producing the electric and magnetic fields that allow it to continue propagating. And that is why we get to see the stars at night. Because light does not need something to travel through. It can just keep going. Now recall, the speed of light is a constant, that lowercase c, 3 times 10 to the 8th meters per second. Right? So if you look at the speed of a wave, how fast is that wave traveling? Well, it goes as the wavelength times its frequency. Or in equation form, we'd say the speed c equals lambda f, wavelength times frequency. So the speed of light is a constant of the universe. So as light propagates, notice how we can think about different colors. Well, that means that if one changes, say the wavelength gets longer, for an increasing wavelength, the frequency must go down because we must keep c constant. So there's this relationship between wavelength and frequency that will keep the speed of light constant. And that's going to lead us into our electromagnetic spectrum.